Hello, Professor Song. I'm here with our last video homework and our first question. I'm so excited to be here and have you seen these questions. So, number one, we have a basketball player makes 80% of her free throws, which is pretty good. Suppose she takes 60 shots. So we're trying to find A, B, and C for this question. The first one asks us to identify our parameters. Very important in the question, identifying the parameters. So we have N, which is going to be the shots she's going to take. So 60, so that's N equals 60. P, which is the percentage she makes, which is 80%. And then 0.20, we find that by doing 1 minus P, so 1 minus the percentage of she makes, so it's 0.8, and we get 0.20. So that's us identifying the parameters. For B, we have to compute the mean and find the standard deviation. So to find this, we plug in the formula. We have N times P equals 60 times 0.80. That gets us 48. So 48 is our mean. That's the answer for the mean. And then to find our standard deviation, we have to take that, divide it by the square root of N times P times 1 minus 9. And that is going to get us 3.10. So that's the standard deviation. Now, the last one for this question one is C. Can normal approximation be used? We have to solve for the formula to see if it's less than or equal or more than or equal to 10. So we do N multiplied by 1 minus P. We see that we get 12. So 12 is greater than or equal to 10, so this is true. And normal approximation can be used. So now we're going to part D. We're going to be using normal approximation to estimate the probability that she makes 50 shots. So now we're trying to find the 50 shots. So we have M equals 48, which is our mean, and standard deviation, which equals 3.10. We're just identifying what we need before we can start doing the question. So now we have to find our z-score. So z-score equals 50 minus 48, because 50 minus the mean that we already had, divided by standard deviation, which is 3.10. We get 0.60. Now to look at our z-table and convert that to our z-score. So I have the z-table here, and when you go on there and look, you'll see that that's going to get us 0.07422, and then to convert that to percentage, and that is 25.78%. And our last one is, and then for E we have reflect, so we can see that it is faster and easier than calculating binomial probabilities by hand, especially with large numbers as we had here. Alright, so for question 2, our question is, a population has a mean of 60 and a standard deviation of 12. Sample of N36 was taken. So that's our question. And then we have A, B, and C, D, and E here. A says, what is the mean and the standard deviation of X bar? So we look at this, we know mu equals 60. So that is our answer to that. And then standard deviation, we have to get 12 from our question criteria and then divide that by the square root of 36, which equals 6. So 12 divided by 6 equals 2. So that's our standard deviation. Now for B, we're finding the probability of a sample mean that is more than 63 plus the z-score. So to find that, we're going to do 63 minus 60 divided by 2, and that gets us 1.5. So 1.5, and then we have to convert that over to find our z-score. So that's the probability. Now converting to the z-score now, we put that into the z-table chart. So when we look at that, we find that it will equal 0.7332. And now converting that into percentage probability for if we get a probability of mean more than 63, we see that equals 6.68%. Now for letter C, it asks us to sketch a bell curve. So as you can see, I've already sketched here before the question was made, before I started the video. But I drew a bell curve, had 60 mils, because that's my mean, and I drew to 63, and I sketched the rest of them because we're trying to find the area more than 63. And this is explained by the central limit theorem, which says if the population isn't normal, the sample mean will be normally distributed if it is large enough. So that's our bell curve. Now, moving on to the last two, we have D. If a sample size equals 100, how would the standard deviation of X change if N equals 100? To find that, we're going to plug into a new formula. Up here we have 36, now we're changing it to 100. So 12 divided by square root of 100, we know that equals 10. So 12 divided by 10 equals 1.2. So that's the answer to that. And we know from looking at this how it changes that a smart standard deviation sample means are more tightly packed around the population mean. So that's how that explains why you get 1.2 right there and how it's decreasing. Now for E, we have to explain the law of large numbers. So the law of large numbers is just pretty much as it increases, the sample mean gets closer to the true population mean. So that's your answer. So question 3 is we have a random sample of 50 students that have an average of GPA of 3.15. We have to assume the population standard deviation is 0.40%. Now, one asks us to construct a 95% confidence interval. So to do that, we're going to plug in our formula, which is x equals z bar times standard deviation over the square root of n, which equals 1.96. So that is going to be our z-score now. So now I use that to find our margin of error. So we're plugging in the formula. 1.96 times 0.4, which is our percentage up here, divided by square root of 50, which equals 0.11. So now we can see that our interval is going to be 3.04, which is our lower bound, comma 3.26, which is our upper bound. Now, number 2, we need to interpret. We can be 95% confident that the true GPA is between this interval, so that's me interpreting it. Number 3, I'm going to sketch up the lower upper bound, so this is our bell curve. Lower bound 3.04, upper bound 3.26, 3.15. That GPA right here being the central area. And then number 4, we're making a 99% confidence interval level. So it's going to increase our wider margin of error since we're increasing the confidence. Our interval now will have the same lower bound, but a slightly higher upper bound since we're making it 99% confident as opposed to 95%. Now the last 2 ones, we have number 5, which asks us to explain why change occurs. So change occurs because our new margin, I'm plugging into this formula here, so we see that it's 1.96 times 0.4 over the square root of 100 equals 10. So 0.40 minus 100 equals 0.078. So now our interval is 3.04.3288. So to summarize, number 6 asks us to summarize. So pretty much higher confidence equals wider interval, as 4 and 5 have already said. And your bigger sample equals a narrow interval. So you have that here, so that's your summarizing. All right, so second to last one, number 4 asks us a soda company says their cans have 12 ounces and sample mean of 40 cans are 11.92 ounces, and our standard deviation is 24. So we have 5 questions here with this. 1 asks us for our null alternative hypothesis, so this is our null up top, and then our alternative is right here. This is one-sided because our mean is less than 12, whereas this one is just equal to. So number 2 asks us to compute the test statistic. So plugging that in, we have z equals 11.92 minus 12. That's our ounces for our sample mean minus the 12, which is our standard deviation. So we have that over 0.24 square root of 40. We get negative 2.11. And then from computing this, we get the p-value of 0.0174. So number 3, we have at the 0.05 level, give the conclusion. So since p less than 0.05, it rejects the null hypothesis because this one's is equal to, but it's less than. So it's not significant there, it's significant here. So there's evidence that the cans are less than 12 ounces because we have this right here since it's less than 0.05. Number 5 asks us to sketch a bell curve and show the significance of this question. So sketch this here. We have 12 because that's our sample mean. So we're just going to shade to the left of that right here, so this is what's shown. Number 5 is asking for the concept. So just shows that it proves that the chance of getting a result this extreme is if HO is true, but it's not. So a smaller p-value like this shows that there's strong evidence against the null hypothesis, and that's concept is proved by going through these questions. All right, so our last question here, number 5, asks us to analysis. The question says, nutritionists test a diet's changing cholesterol from 200 milligrams, sample equals 15, mean equals 194, and standard deviation equals 20. So these are things that we know before getting into the question. So number 1 asks us to state the null and alternate hypothesis. So this is our null. We see the mean equals 200, and then we see for our alternative we have 200, but it has to be equal to. So or not equal to, so that means it'd be a 2-sided test. So number 2, we have test statistic / the degree of freedom. So to test this, we'll have t equals 194 minus 200, our mean minus 200, because that's what we get from our milligrams right here, the change in cholesterol, divided by 20 divided by the square root of 15. That's our squaring our sample, and then 20, our standard deviation. We see that we get negative 1.94. So that means our degree of freedom using from that is 14. That's the change. Now we move to number 3, which asks us for the critical value. So we take our degree of freedom, which is 14, at A equals 0.05. So now if we transfer that over to T, we find it equals plus or minus 2.145. So now that leads us into our next part where we sketch our bell curve. So looking at our rejection zone, again, we have plus or minus. So we have minus 2.145 and plus 2.145. So if the score ended up being on a test, the change in cholesterol, if it was underneath negative 2.15, it'd be shaded, it'd be an rejection zone. If it's over 2.145, it's an rejection zone because it's over. So we shade that part, shade that part. You can see that this change here is 1.94, so it's not in the rejection zone. Number 5 asks us for a confidence interval. So we got T equals 2.145. We got here our margin equals to 2.145. We had here the rejection zone, so lower and upper bounds, times 20 divided by the square root of 15, which equals 11.07. So now we use that to know the interval. We can find that it's 182.7393, comma 205.07, our lower and upper, and that includes the 200. So we can see because we see number 6, comparing T versus Z, we see that both compare samples to population, so they can both be used. They stray a little bit because T is used in population, ST is unknown, and sample size is small, so that's where T strays from Z.